In polarizing power, I told you one formula, that is phi. What is phi? Ionic potential. मैंने बताया था कि नहीं, याद है?
Yes, sir.
हाँ सर.
Ionic potential. So ionic potential is what? Tell me.
So charge by size.
Yes, charge by radius you can take. Size is radius. Okay. Charge of cation. What is the charge? Maybe 1, 2, 3, 4, etc. Charge by size. Size I am writing radius. Size you write or radius you write, whatever. And size you take in angstrom. Okay. Charge plus 2, plus 3, plus 1, plus 4, like that. This is called ionic potential. And you calculate ionic potential. Okay. Then you find the square root of ionic potential. Square root. So if you find square root, the various values will come for different type of metallic oxide, non-metallic oxide. Okay. So for different metallic oxide or non-metallic oxide, for oxides, I'm writing oxides, maybe metallic, non-metallic. For different oxides, if square root of phi value is coming greater than square root of phi is coming greater than 3.2, means very high. If polarizing power is high, what will be covalent character? Covalent factor will be high or low?
High.
High.
Covalent character will be high. If covalent character is high, then it will be acidic. So if square root of phi is coming more than 3.2, then that oxides will be acidic. Then the oxide is acidic, you can write. Then oxides, that particular oxide will be acidic. Will be acidic. Okay. Now number 2. Point number 2. So point number 2, suppose square root of phi is coming in between 2.2 and 3.2. So this is coming in between 2.2 till 3.2. Okay. If it is coming in between these two, then you say the oxide is amphoteric. The oxide will be amphoteric. Will be amphoteric. Amphoteric. Okay. Now next point number 3. Suppose square root of phi is coming less than 0.2. It is coming less than 2.2. Then what we say? Then oxide will be basic. Why? Because polarizing power is poor, less. So less means covalent character is less. Then we say the oxides of that element will be what? Will be
Yes.
basic. Remember this. Based on this value, we can also predict whether an element oxide, means nitrogen oxide, is acidic. Carbon monoxide is basic. Okay. So whatever oxide, acidic or basic, we can tell by seeing the electronegativity difference. Okay. If electronegativity difference is high, then accordingly we can tell whether oxide is basic, acidic or amphoteric. Okay. Now let us take example. Suppose beryllium oxide will take. Okay. Beryllium oxide will take. And then we will take aluminium oxide. Okay. Then we will take, say, magnesium oxide. Okay. Then we'll take nitrogen pentoxide. So nitrogen pentoxide means you take the charge of beryllium 2 plus. Here charge of aluminium 3 plus. Charge of Mg2 plus. Charge of N2 plus. N5 plus it will come. Okay. So this charge by its radius if you calculate and square root if you make, for beryllium it is coming 2.54. For aluminium it is coming 2.45. For magnesium it is coming 1.66. For nitrogen it is coming 10.66.
So this is the root 5 value.
Yes. So if you find square root of 5 value. So if it is coming 2.54, then what you say? It is acidic, basic or amphoteric?
Sir, amphoteric.
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 A am writing.
Amphoteric.
Is this one aluminum oxide?
Amphoteric.
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 Magnesium oxide?
Basic.
It's
Basic.
basic.
Nitrogen oxide?
Acidic.
It's acidic.
Acidic. Clear?
Yes, sir.
So if you are available values, then you can tell this all. If you don't have available value, then telling this all is difficult. Okay, clear? Is this clear?
Yes, sir.
Now I'm going to next page. Next.
Sir,
Yes.
so if we had predicted just by our previous knowledge with increase in charge, polarization increases.
That also will help.
So then it will slightly be different, no? The order.
Charge means this is more charge.
Yeah. So
This is less charge. This is more charge. More charge means acidic. And this is less charge means basic. This is more charge means amphoteric. This is also +2. So these two we cannot predict. Okay. This is only the final. Is relative order we can predict. See, based on concept, we can predict the relative order, but exactly which is acidic, which is basic, which is amphoteric, that we cannot predict. Relatively, which is stronger, which is weaker, that we can predict. But final is this value. This value is coming in between this, then we can tell which is amphoteric, which is acidic, which is basic. Is that clear?
yes, thank you.
So after that, next you write thermal stability of ionic compound. Thermal stability, right? In thermal stability, I will give you a notes.
तो थर्मल स्टेबिलिटी शायद किए थे पिछले क्लास में.
हाँ किए थे और थोड़ा उसका एक्सेप्शन भी है तो इसलिए मैं नोट दे रहा हूँ. थर्मल स्टेबिलिटी उसका 2 पॉइंट है. मैंने एक पॉइंट दिया फाजन रूल से कैसे होगा बता दिया. लेकिन उसका अगर ये होता है लैटिस एनर्जी डोमिनेट होता है तो क्या होगा उसके हिसाब से बोलना है. ओके सही है. तो थर्मल स्टेबिलिटी हमें देखना है. तो थर्मल स्टेबिलिटी कैसे देखेंगे. पॉइंट नंबर 1 लिखो. पॉइंट नंबर 1 for binary compounds having smallest stoichiometric ratio. For binary compounds, having smallest stoichiometric ratio, the thermal stability order is decided by
Sir, please repeat once again.
for binary compounds having smallest stoichiometric ratio, the thermal stability order is decided by the interionic distance. Larger the interionic distance, lower will be lattice energy. And lower the lattice energy, lower will be thermal stability. So let us take beryllium oxide, magnesium oxide, calcium oxide, strontium oxide, barium oxide. Okay. So you tell me lattice energy is maximum in which case? Beryllium oxide or barium oxide?
So beryllium oxide.
So lattice energy order is like this. This is the order of lattice energy. And what is the order of polarization? Tell me.
The opposite.
So polarization order is like this. But melting point, if you see, the melting point of beryllium oxide is more. It's coming in polarization order also, no? Polarization order is reverse. Lattice energy is more. Polarization. Acha, polarization of beryllium oxide is also more, na? Smaller size of pattern. Tell me.
Yes, sir. First MG, then B.
Yes.
Yes, sir.
So lattice energy order is this, and polarization order will be reverse. Polarization order will be like this. Like this. Polarization order is like this. Lattice energy order is like this. So if polarization is more, its melting point should be least, but its melting point is more. Because oxide is small anion, so small anion means polarization is not dominating. If polarization is dominating, we should see the order in terms of polarization. Here we will see the order in terms of lattice energy. So lattice energy is opposite of polarization, but lattice energy is dominating. If lattice energy is dominating, then what can we say? We can say the order of lattice energy is also order of melting point. So this is against the polarization. Is that clear? So in oxide, in hydride, in fluoride, in nitride, the order will be according to order of lattice energy, remember, because they are small what anions. Here polarization is not dominating, it is not much more effective. So the order of melting point is decided and thermal stability is decided by this. So thermal stability of beryllium oxide is more than magnesium oxide, than calcium oxide, than strontium oxide, because lattice energy is more. So lattice energy is directly proportional to thermal stability. Is that clear? Bro,
हाँ सर.
more the lattice energy, more energy required to break, more will be high temperature to required to break, so more will be thermal stability. So if lattice energy is more, force of attraction is strong, high energy required, more energy required to break, and so thermal stability is more. So for these anions, you can decide the order of thermal stability based on lattice energy. Okay?
Sir, can you repeat this part again?
Yes, I am taking one more example. Suppose these anions you are taking, these anions are very small. The small anions for condition for polarization is anion should be larger anion. If anion is larger, then what can you say? If larger anions are there, then polarization will be dominating, effective. Polarization will be much more pronounced. If anion size is larger, polarization will be much more pronounced. If polarization is much more pronounced, then order of thermal stability, order of melting point will be based on polarization. But here the size is small, polarization is weak, polarization is small. If polarization is small, then you see the lattice energy. So lattice energy is more. If size is small, then lattice energy is directly proportional to charge, and lattice energy is inversely proportional to distance. If size is small, if anion size is small, distance between cation and anion also will be small. If distance between cation and anion are small, lattice energy will be more. If lattice energy is more, then they will be stable, thermally stable, and also melting point high. Is that clear?
Yes, sir.
So that's why smaller anions, if you take, lattice energy will dominate. Here, the order of thermal stability is based on lattice energy, not based on polarization. Okay. Some
Yes,
more
sir.
example of
Yes, sir.
this category I am taking. Lithium nitride you take, sodium nitride you take, lithium nitride, sodium nitride, and potassium nitride. You say thermal stability, which is more? Lithium nitride, sodium nitride, potassium nitride.
Lithium nitride.
Yes, because distance
Lithium nitrate.
distance between lithium and so nitride is small. Sodium and nitride is little more. Potassium and nitride is more. So distance increases. If distance increases, lattice energy decreases. So lattice energy decreases. If lattice energy decreases, thermal stability also decreases. Is that clear? Tell me.
Yes, sir.
Suppose you take lithium oxide you take, sodium oxide you take potassium oxide, you take rubidium oxide. Okay, these all notes I'll give you, don't worry. Handwritten notes or typed notes I'll give you, nothing to worry. Thing is that you try to understand. When I give notes, you read again and after reading you can understand and you can remember also. Okay, so in these anions your lattice energy order will be order of thermal stability and also melting point. So lattice energy decreasing like this is the lattice energy order, and you know that lattice energy is directly proportional to thermal stability. More the lattice energy, more thermal stable. More the thermal stability, okay, more temperature required to break. So thermal stability order also like this. Is that clear?
Yes, sir.
So completed factor number 1 completed. So I'm going to factor number 2.
Okay, sir.
So suppose your anions are big anions. Anions are like perchlorate, chlorate, hypochlorate, hydroxide, nitrate. Big anions you are taking. If you take big people, so big people do not follow rule. Okay. Small people like us only follow rule. We are sincere and sincerely hardworking, isn't it? And big peoples are hardly working, isn't it? So these are big anions. They do not follow the rule of lattice energy. They follow the rule of polarization. What rule? Polarization rule. Why?
Right.
Why they follow polarization rule? Tell me.
So because they're big in size.
Yes,
So
because
the
of
lattice energy is small.
yes, their lattice energy is strong, so small, extremely small. This factor of lattice energy is squeezing, is less dominating. So you have to see which factor is dominating. The order will be according to that factor. For these big anions, the polarization is very effective and much more strong. So if polarization is strong, then what can you say? The order of thermal stability is based on the polarization. More the polarization, less thermal stability. So what can you say? Tell me. Thermal stability, inversely proportional to polarization or covalent character. Don't get confused. Chemistry is itself is a confusing subject. So in chemistry, so much variation, so much exception will be there. But you fix your mind. What is what? In what case what will dominate? In what case what other things will dominate? If you fix up those things, then everything is clear. In exam, question from the clear concept will come. Okay, polarization. समझ में आ रहा है कि नहीं? Polarization. So thermal, I am using mouse to write these letters, so handwriting is not good. So you try to manage. Thermal stability is inversely proportional to polarization. More the polarization, more covalent character. You can say it is also inversely proportional to covalent character. Character writing CH. Okay. So more the covalent character, less will be thermal stability. Okay. So now you tell me what is the thermal stability order of LiClO3, NaClO3, KClO3. You tell me which order, what is the order, increasing or decreasing? Tell me. Acha, tell me the order of polarization.
Thermal, sta- thermal
Covalent
stability is increasing.
increasing. Yes, very good. Covalent character order. Tell me first. Covalent character
Decreasing.
decreasing. Yes, very fine. Covalent character is decreasing, is like this, is like this, is like this. Then you tell me thermal stability what order? thermal stability order is increasing. Yes. All of you understood or not? Tell me.
No, sir.
Not understood.
No, sir.
No, sir.
See, two things you keep in mind. If size of anion is small, okay, and size of anion is big. If size of anion is big, then polarization is strong. Polarization is strong. Tell me, if
Yes, sir.
size of anion is big, polarization is strong, or size of anion is small, polarization is strong.
Size of iron is big.
Size of anion big. If size of anion is big, then polarization strong means polarization will be much more effective, and the order will be in terms of polarization effect. If anion is big and anion containing whatever cation, if anion is big, if you are comparing with these type of anions and salts, then the order of covalent character, if covalent character is more, thermal stability is less. Why? Because more covalent means with less temperature it will break, it will decompose. So thermal stability is less. That we studied in the last class. We have discussed already. Okay. So if polarization is more, then our thermal stability will be less and its decomposition temperature will be less. Okay. So we have seen the covalent character is decreasing. If covalent character is decreasing, thermal stability is inversely proportional, so it will be increasing. Is that clear?
How is the covalent character decreasing? I cannot understand that.
Covalent character, why decreasing? See, smaller size of cation, greater covalent character. Bigger size of cation, lesser covalent character. Still bigger, covalent character decreases. We have studied. Smaller the
Oh,
size
yeah.
of cation, more covalent character. Bigger the size of anion, more covalent character. Charge on cation anion, more covalent character. Pseudo inert gas configuration, more covalent character. Non inert gas configuration, high covalent character. We have studied already. Yes or no?
Yes, sir.
Now understood though.
Yes, sir.
So if you do not understand, don't hesitate to ask me. I'll explain again and again. But thing is that you should understand. Concept should be clear. But at the same time, you have to revise at home also. Okay. Now suppose I am taking carbonate, beryllium carbonate. I am taking beryllium carbonate, magnesium carbonate. Let us take magnesium carbonate. Okay. Let us take calcium carbonate. Let us take strontium carbonate. Let us take barium carbonate. You tell me what is the order of covalent character.
Decreases.
Sir, decreasing.
Yes, yes,
Thermal
yes, very
stability
good.
is increasing.
Covalent character is decreasing. Yes.
Yes.
So covalent character is decreasing. So what will happen to thermal stability? Tell me.
Increases.
Increases,
Yes,
sir.
thermal stability increases. It is inversely proportional. Thermal stability increases. Is that clear?
Sir, after strontium carbonate, what is that?
Barium carbonate.
Okay,
Barium.
okay.
Okay. So like this, whatever anions are there, you can compare the same order and inversely proportional to polarization, inversely proportional to covalent character, the thermal stability one. Is that clear? But remember, if the anions are these anions, small sized anions, in that case you do not apply polarization because polarization is silent, very less effective. Polarization is dormant in this case, okay, very negligibly small. If polarization is negligibly small, the order will not be in the order of polarization. If you apply, it will be wrong, answer will be wrong. So you should apply the order of lattice energy. What? Lattice energy. But here why can't you apply lattice energy? If size of anion is big, then lattice energy is very less because lattice energy inversely proportional to size. Inversely proportional to size of anion. But polarization is directly proportional to size of anion. So size of anion big means lattice energy is negligibly so small. So here lattice energy will not be dominating. Here polarization will be dominating. But in this case, your lattice energy will be dominating. So if lattice energy is dominating, in that case, the order of lattice energy will be order of thermal stability and order of melting point. So beryllium oxide, magnesium oxide, calcium oxide, if you see lattice energy, so lattice energy decreases because size of cation increases. If size of cation increases, size is inversely proportional to lattice energy. So lattice energy decreases. If lattice energy decreases, and here lattice energy is directly proportional to thermal stability, because more the lattice energy, more energy required to break, more will be the stability. So thermal stability is directly proportional to lattice energy. So lattice energy order decreasing, thermal stability order also decrease. But if you apply polarization, it will be inverse. Polarization is this is this is greater than this. So beryllium oxide polarization is more than magnesium oxide. Magnesium oxide polarization more than calcium, because smaller size of cation beryllium, then magnesium, then calcium 2 plus, then strontium 2 plus, then beryllium 2 plus. If size of cation increases, polarization decreases. So this is also order of polarization. If order of polarization is there, order of melting point and order of thermal stability should be inverse. But it is again same. Why same? Because here polarization has very less significant effect. Is that clear? Tell me. So these things you have to remember. In these anions you apply lattice energy, but these anions, big anions, you apply polarization effect. So now the concept is clear. The questions will come from this Fajon's rule. Okay. Notes of Fajon's rule I'll give you. Don't worry. Okay. So after the class, you go through the notes, you read again, and whatever I taught you, you revise, because inorganic is volatile subject, just like alcohol, just like petrol. Suppose you pour petrol in an open container, after 5 minutes no petrol will be left. Have you done like this? So
Yes,
कार्बोलिक
sir.
कार्बोलिक एसिड के साथ किए थे.
yes, hand sanitizer. You see, sanitizer nowadays you might be using sanitizer. Sanitizer only alcohol. So you know that sanitizer we can prepare at home.
Yes, sir.
So if you prepare sanitizer,
Yes,
the
sir.
50 rupees sanitizer can be prepared at 10 rupees at home. So you can prepare same amount of sanitizers at 10 rupees at home. They sell in 50 rupees. You think that whatever higher price they are using. So the sanitizers preparation I tell you within 1 minute. Do you want to know?
Yes,
Sir,
sir.
Yes, sir.
Yes, sir. You can tell.
So there are different type of sanitizer preparation. Different brand are using different sanitizers. In sometimes they are using some gel, sometimes they are using some scented material. But actual sanitizer which is used for germicide, means kills germs and like coronavirus also. So those type of sanitizers are based I what quantity and what proportion and what type of chemical. I'm telling you, first you should take ethyl alcohol. You can take isopropyl alcohol also. Okay, you take ethyl alcohol. Okay, this is first number one. Number two, you can take distilled water. Don't take tap water. Distilled water is 100% pure. Okay, distilled water you should take. Then third one, you should take glycerin. In winter season, you might be using glycerin. Glycerin. Okay. And fourth one is your hydrogen peroxide. This is the best sanitizer, medicated sanitizer. Some people are using some gel, so and some perfumes, so it looks attractive. But this is the medical prescribed sanitizer. But now how to mix? Okay, how to mix them? So you can take 80% by volume. This you take 80% by volume of ethyl alcohol. Okay, and hydrogen peroxide you take 5% by volume, and this you take 5% by volume. So it becomes 90, 10% you take distilled water. I prepare sanitizer at my home and I distribute it to some of my friends. Okay. At my home,
Wow, sir.
I've taken many
But
branded sanitizer also. I purchased many branded sanitizer. I was seeing what are the composition. They use different composition. Okay. They use so many composition, but this is the best sanitizer. In some sanitizer you find these four. These four are best. So what you can do? How to first you take glycerin, because this is the most viscous. First you take glycerin, pour in the mixing chamber wherever you want to mix. There you pour 5 ml glycerin, you pour. After 5 ml glycerin, then you add 5 ml H2O2 into glycerin. Glycerin में 5 ml H2O2 दे दो, ठीक है? Take glass rod only for mixing. Don't use spoon. Don't use anything. Glass rod in your laboratory available, and you use only glass vessel for mixing. Means beaker ले लो, कोई भी glass vessel. तो glass vessel ले लो, glass rod ले लो. इसको 5 ml, इसको 5 ml ऐड कर दो. ऐड कर दिए. उसके बाद ऐड करो, उसके बाद डिस्टिल वाटर ऐड करो 10 ml. तो ये पहले, ये दूसरा, ये तीसरा लेना है. At last you add ethyl alcohol. After adding, you do stirring properly. After that you pour in a bottle. इसको बॉटल में ही डायरेक्ट ले सकते हो, कोई प्रॉब्लम नहीं. बॉटल में भी ये प्लास्टिक बॉटल ऑल्सो, ग्लास बॉटल इज बेस्ट, बट प्लास्टिक बॉटल ऑल्सो यू कैन टेक. तो देन यू क्लोज द माउथ. तो उसका जो स्टॉपर है बंद कर दो. बंद करके उसको क्या करो, यू मेक इट हॉरिजेंटल. ओके, हॉरिजेंटली ऐसे रखना है. हॉरिजेंटली ऐसे रख के इसको इसको फिक्स करना है. इसको एक हाथ को यहाँ पे फिक्स करना है, दूसरे हाथ को क्या करना है, इसको रोटेट करना है. जस्ट रिंज इट. द रिंजिंग इज लाइक दिस. यू हैव टू रोटेट दिस, rotate, and after some time you fix this hand, and this also you rotate. Both way you rotate clockwise 5 rotation and anti-clockwise 5 rotation. Then you fix this. Then you rotate clockwise 5 rotation, anti-clockwise 5 rotation. And if you do this several times, 3 to 4 times, then your sanitizer is prepared. But it is not usable at instantly. Once it is prepared after mixing, you keep it for at least 2 hours. 2 घंटे के बाद इसको यूज करोगे तो काम आएगा. Is that clear? So now you can try this at home. This is not harmful. No chemical is harmful. Okay, only alcohol is harmful. If you bring flame to it, this is very, very dangerous. It will immediately catch fire. Okay, this is only harmful, and this is all not harmful. But
So
nothing.
when to give that alcohol?
Pardon?
Sir, when to give that alcohol? Then sir,
Last,
कब देंगे
last.
वो alcohol को पहले देंगे और लास्ट पे?
लास्ट में अल्कोहल ऐड करना है. पहले ग्लिसरीन ऐड करना है, इसको पहले ऐड करना है ए, इसको सेकंड में ऐड करना है बी, इसको थर्ड में ऐड करना है सी, लास्ट में अल्कोहल ऐड करना है. ऐड करने के बाद उसको क्लोज माउथ में रखना है. जो जो बॉटल से जो आता है मार्केट से, उसी बॉटल में प्रिपेयर कर सकते हो. मैं अभी 100 ml का प्रिपरेशन बताया. 100 ml. सपोज यू गॉट 50 ml. Suppose you have 50 ml bottle you want to prepare, then take all half of this amount. ठीक है, इसका exactly half amount ले लो. ठीक है, और इसमें तो
सर ये जो ऑर्डर में डालना है उसका कोई मतलब कारण है?
हाँ, इसका कारण है मिक्सिंग अच्छा से होगा. ग्लिसरीन ज़्यादा विस्कस है, ये जर्मीसाइड है, ये वायरस को किल करने के लिए हेल्प करेगा, और अल्कोहल भी हेल्प करेगा. अल्कोहल और हाइड्रोजन पेरोक्साइड. ग्लिसरीन क्या करेगा, इसको विस्कोसिटी बढ़ा देगा. डिस्टिल वाटर इसको मिक्स करने के लिए रहता है. अच्छा, मैंने गलत बता दिया. सॉरी, आई टोल्ड रॉन्ग. दिस इज 10%, दिस इज 80%. सॉरी, अल्कोहल इज 10%, distilled water is 80%. Okay. So now let's move to next. Okay. So here all theories are over. So all theories are explaining the shape of molecule, stability, hybridization, their bond angle, and then the formation. Okay. After all theory has come, there are some drawbacks in all theories. So some drawbacks were there in all valency bond theory, valency shell electron pair repulsion theory, and back bonding. Back bonding तो हो गया था ना?
हाँ
Yes.
सर
So some questions of back bonding I gave that attachment. I will give notes again. In that I will include back bonding. That the picture was not clear, so I will give you that back bonding notes. Okay, that is okay. Now I tell you the new theory, that is molecular orbital theory. Okay, so right, molecular orbital theory, MOT, इसको बोलते हैं MOT, molecular orbital theory. Molecular orbital theory. Okay. Now question arises, why we need a molecular new theory? Already we have so many theory, isn't it? We can use so many theory to explain the bonding. But why we need one more theory? Already we have studied so much, we have studied in this chapter. नहीं और भी पढ़ना है कि नहीं?
Yes, sir.
See, in all theories we studied so far are unable to explain the magnetic properties of molecules. Number one क्या drawbacks है? Magnetic properties are not being explained. Magnetic properties. Okay. So no need to write because I cannot write properly. So our notes I'll give you, I'll explain. Okay, just you listen. Okay. तो मैग्नेटिक प्रॉपर्टीज हम लोग एक्सप्लेन नहीं कर पाए. क्या मैग्नेटिक प्रॉपर्टी? मैग्नेटिक प्रॉपर्टीज मतलब पैरामैग्नेटिक एंड डायमैग्नेटिक. जो एटॉमिक स्ट्रक्चर में हम लोग थोड़ा बहुत जान लिए, वो एटम का जाने थे, अभी मॉलिक्यूल का जानेंगे यहाँ पे. पैरामैग्नेटिक एंड डायमैग्नेटिक. ओके. So paramagnetic substances are those substances which are weakly attracted by external magnetic field. So if you keep external magnetic field, it will be attracted towards the external magnetic field. Okay, those are known as paramagnetic substances. Oxygen is paramagnetic substance. Oxygen plus also paramagnetic. Oxygen but it is found surprisingly, oxygen 2 plus is diamagnetic substance and oxygen 2 minus is diamagnetic substance. These are diamagnetic substances. What is diamagnetic substance? Diamagnetic substances are those substances which when kept in external magnetic field, they repel, they tends to oppose the magnetic field of external magnet, and this is known as diamagnetic substance. And we told in atomic structure is that substance which have unpaired electrons, they are paramagnetic, and substance which have paired electrons, they are diamagnetic. But in oxygen, suppose you take oxygen, O double bond O. We made O double bond O? Made or not? So Lewis structure says O double bond O like this. This is Lewis structure. And orbital diagram also telling this. So here this electron is paired, this is paired, this is paired. So two lone pair and two bond pairs are there. So these all electrons are so paired. It should be diamagnetic, but it is paramagnetic. How it is paramagnetic? So this cannot be explained by valency bond theory, nor valence electron pair repulsion theory, not Bend's the rule, whatever. It cannot be explained by any theory. So number one drawback. Number two drawbacks, why He2 not possible, but He2 plus is possible. He2 plus exists. So He2 not possible, we are saying no, force of repulsion dominates and force of attraction is less. So He2 not possible, we are explaining by theory. But no mathematical explanation, no explanation by any concept, any logic, by any theory. He2 not possible, valence bond theory is not. Valence bond theory is telling that He is having paired electrons. Only unpaired electrons overlap, atomic orbital overlap. So unpaired electron becomes paired to form bond. And here already paired, so it will not form bond. So if it is not forming bond, He2 plus how exists? Valence bond theory is silent about this. Okay, is that clear? Now number 3 drawbacks, that is major drawbacks. Major drawbacks, it is telling that the electron is showing wave nature, isn't it? If electron is showing wave nature, whenever atomic orbital overlap, atomic orbital combine, when two atomic orbital overlap, two atomic orbital combine, then definitely the wave of electron must be considered, and the nature of wave, intermixing of wave must be taken into account. So here we have not taken the wave, we have taken the shape of orbital by Schrodinger wave equation and solved. That is up to some extent we are using wave equation and doing. But actually the electron wave, if mix, if two waves are mixing, there are two type of mixing. One is mixing showing a maxima and mixing showing a minima. Maxima is known as antinodes. Maxima is giving antinodes and minima is giving nodes. So whenever electrons are mixed together, they will mix by constructively, meaning constructive interference. Means electron mixing is known as interference of wave. That is there in wave motion chapter. You have studied in 9th, 10th, or you will be studying in 11th, 12th. 11th class only wave is there. So constructive interference of wave. When waves are mixing, they will mix by constructively or they will mix by destructively. So destructive interference of wave. So whenever these waves are mixing, these waves mix and there must be combination of atomic orbital due to mixing of wave. And we should use more and more wave nature that we have not used. So that is the drawbacks in the past theory. Fourth drawbacks is what? Fourth major drawbacks is if atomic orbital combine. See, chemical bond is a chemical change. It is not a physical change. When chemical change occurs, then new substances are formed and the properties of old substance will be lost that you are studying from your childhood. Okay, so when a chemical bond is formed, definitely two atomic orbital combine, they should give molecular orbital. They should give what? Molecular orbital, and molecular orbital shape. Okay, molecular orbital shape, energy, stability, and electron overlapping definitely should be different from atomic orbital, and the properties should be changed. Properties will not be same, properties should be changed. So that is told, that drawback that we have not taken into consideration. Next, point number 5. Whenever two atoms combine, there exists two type of force. One is attractive force, one is repulsive force. We have considered the attractive force into more discussion, but we have ignored the repulsive force. Here repulsive force also play a vital role in forming a chemical bond that we have not considered. So due to this, we need a new theory that is known as molecular orbital theory. Next, drawbacks.
What is the last point, the fifth one?
Fifth one.
Yes, sir.
Oh, fifth one. What I told? Attractive and repulsive force. Okay. Fifth one I told about attractive force and repulsive force. Attractive force and repulsive force. So there exist two type of force: attraction between nucleus of one element and electron of other, and repulsion between electrons also there, nucleus also there. So that must be considered. but that is ignored. In this theory, that is not considered, that is ignored. So we have to consider all the theory or all the forces, then only our concept will be clear. So this is number 5. Then point number 6 you write. So relative stability of different ions, relative stability of different ion. कौन सा आयन है? O2, O2 plus, O2 minus, O2 2 minus. So relative stability of different ions. N2, N2 plus, N2 minus. Okay. Bond order cannot be determined from this directly, but by this theory we can find bond order. Okay. So all these are drawbacks. So that's why we are taking a new theory. That theory is known as क्या?
Molecular orbital.
Molecular orbital theory.
Orbital theory. So in molecular orbital theory, so electrons are taken as wave function. Okay, electrons are taken as wave function, and this theory is explained by LCAO. LCAO means linear combination of atomic orbital. How atomic orbital combine, that is made a sub theory, that made a rule, certain rule, that is known as linear combination of atomic orbital. I'm not writing, I'm saying these notes I'll give you. Okay, linear combination of atomic orbital. Is that clear? So linear combination of atomic orbitals, how possible? So that is possible by considering electron as wave. Okay, suppose electron, one electron wave for one orbital is psi a. Psi a is the amplitude of electron wave. Amplitude of electron wave of one orbital. And psi b, we are taking another amplitude of electron wave of another orbital. Okay, clear? So these two electron wave, when mixed together, so chemical bond is formed due to overlapping of atomic orbital. So electron wave must mix together. When overlapping of atomic orbital takes place, electron wave must mix together. If electron wave will mix together, let us take example of how electron wave are mixing. Suppose one wave is going like this. Okay. And another wave is also going like this. They can mix. Suppose this is plus, this is plus, this is minus, this is minus. This is going in downward direction, so minus. This is going in up direction from the mean position, plus. So suppose these two waves are mixed like this. This is plus, this is minus, but this is minus and this is plus. Okay. So one electron wave is going up, but the same time it is going down. When it is going down, same time it is going up. So these two electron wave can mix. So in valence bond theory, what is told? Say s orbital will mix plus, we can mix with plus, and plus can mix with minus. Or say if it is p orbital like this, so this side plus, this side minus, can mix with this side plus and this side minus. Now suppose this one, we can take this side plus, this side minus, can mix with this side This side minus, this side plus. Understood or not? Are you able to follow?
Yes, sir.
See,
Yes, sir.
the toughest part of this chapter is MOT, molecular orbital theory. Okay. So listen carefully. So when electron waves are mixing, we studied that the electron wave will be plus plus, or this plus is approaching plus. This way they can mix, or plus can mix with minus, or in p subshell plus is mixing with minus, this way. So when these electrons are mixing, they can mix by either way, either this way or this way. So when this way is mixed, then after mixing, the shape of the orbital will be different, because when atomic orbital will mix, this is atomic orbital, this is another atomic orbital. These two atomic orbitals of same atom or different atoms possible. When two atomic orbital mix, then you will get, this is the mixing. After mixing, you will get molecular orbital. What you get? Molecular orbital. So molecular orbital shape, energy will be entirely different from atomic orbital. So molecular orbital, when mixing, these electrons will be added. The amplitude are in same direction. The amplitude will be added. First I am showing the wave of amplitude. Then I show you orbital. So this amplitude when added, this plus plus added, this will be like this. Can you imagine? Tell me. If you mix like this, you will get two amplitudes are added. So resultant wave, when two electron wave are mixing, interference of two electron wave give you resultant wave. The resultant wave is called molecular orbital. So that molecular orbital amplitudes are added. So if this amplitude is say psi A and this amplitude says psi B, maybe psi A, both are psi A, that is also possible. These are added. And this is minus. So this is plus and this become minus. Okay. So these amplitudes are added. So you say psi A plus psi B. Okay. Now when two electron wave are taken like this, psi A and psi B. But this psi B is minus psi B. Minus psi B. So what you say, psi A plus minus psi B. This is minus of this, na? So psi A plus minus psi B, you can say addition subtraction is same for plus and minus. So we can say plus into minus is minus, psi A minus psi B also you can tell. So psi A plus psi B possible when the mixing takes place. Here also mixing can give you psi A minus psi B. If psi A minus psi B, this is say psi A, this is psi B. Suppose psi A is bigger than psi B, after subtraction you will get like this, very small amplitude. The difference will be left. So this is called psi A minus psi B. This is the resultant electron wave of two combining orbital. So this is molecular orbital. But molecular orbital, when they are mixing constructively, this is constructive interference. So in physics you will study, due to mixing of two wave, there will be two type of interference. One is constructive interference, another is destructive interference. In constructive interference you will get maxima, that is antinodes. And if you get destructive interference, that will give you minima, that is called nodes. If electron wave is 0, then it is node. Suppose psi A, psi B both are same, so psi A minus psi B is equal to 0 you will get. So they will give molecular orbital. This molecular orbital in first case is known as bonding molecular orbital. In second case, you will get anti-bonding molecular orbital. Okay. So psi,
Sir,
yes.
sir, please repeat this part.
So see, when two electron wave are added, they will give you interference. Interference means mixing of wave. Mixing of wave will give you two type of mixing, where amplitude are added, where amplitude are subtracted. If amplitude are added, then it is called constructive interference. Give you maxima, antinodes. When amplitudes are subtracted, that is called destructive interference of electron wave. And destructive interference of electron wave give you minima, nodes. The molecular orbital, that name is known as anti-bonding molecular orbital. And in constructive interference, when it gives antinodes maxima, that is called bonding molecular orbital. So it is told that whenever two atomic orbital overlap, the electron will give you bonding molecular orbital also, anti-bonding molecular orbital also. Both will give. The bonding molecular orbital and anti-bonding molecular orbital both will give. When both will give, the electron will mix. One case there will be force of attraction. This will be having force of attraction for bonding molecular orbital. For anti-bonding molecular orbital, there will be having force of repulsion. The attractive force, repulsive force are also taken into consideration in case of molecular orbital theory. Okay, I am going to next page. Right. So what is told? The psi are resultant for bonding molecular orbital and psi are resultant for anti-bonding molecular orbital. Two molecular orbital we got anti-bonding ABMO, BMO. Bonding molecular orbital psi A is psi A plus psi B. Is that clear? And anti-bonding molecular orbital, it will be psi A minus psi B. But this is the electron wave amplitude. We want to find the probability of finding electron, means probability density. The probability density for bonding molecular orbital will be square of this or not? Square of this. So this will also be square of this.
So what did you say? Please repeat it once more.
See, psi square gives you the idea about probability density of electron, isn't it? Psi
Yes, sir.
gives you idea about amplitude of electron wave, but we want to know the probability of finding electron in a particular region in space, three-dimensional space. So let us make it square. So if you make it square, psi resultant bonding molecular orbital will give you psi a square plus psi b square plus 2 psi a psi b. And for antibonding molecular orbital is coming psi a square plus psi b square minus 2 psi a psi b, isn't it? Tell me.
Yes, sir.
So that means psi square for bonding molecular orbital. Psi square for bonding molecular orbital is greater than psi a square plus psi b square. And psi resultant for anti-bonding molecular orbital is less than psi a square plus psi b square by this value. By this is more by this value, this is less by this value. Is that clear? Means psi a square क्या है? The probability density of electron wave of A. Psi b क्या है? Probability density of electron wave of psi b. तो दोनों का प्रोबेबिलिटी डेंसिटी इलेक्ट्रॉन से बॉन्डिंग का मॉलिक्यूलर ऑर्बिटल का इलेक्ट्रॉन डेंसिटी ज्यादा हो जाएगा बॉन्डिंग मॉलिक्यूलर ऑर्बिटल में। एंटी बॉन्डिंग मॉलिक्यूलर ऑर्बिटल में क्या होगा, दोनों का इलेक्ट्रॉन डेंसिटी जो पहले जितना था उससे कम हो जाएगा by 2 psi a psi b। इज दैट क्लियर? दैट मीन्स अगर दो इलेक्ट्रॉन वेव अगर मिक्स हो रहा है, that means when two electron wave are mixing, then what will happen? Then electron density may increase, may decrease. If electron density will increase, then we will get bonding molecular orbital, decrease anti-bonding molecular orbital. So that means when two atomic orbital overlap, it will give two type of orbital. One is bonding molecular orbital, another is anti-bonding molecular orbital. Okay, what is the difference between these two? बॉन्डिंग मॉलिक्यूलर ऑर्बिटल एंटी बॉन्डिंग मॉलिक्यूलर ऑर्बिटल का क्या डिफरेंस है? दोनों का क्या डिफरेंस है? दोनों का जो डिफरेंस है वो हम लोग यहाँ पे देखते हैं। तो वन, अच्छा कुछ डायग्राम कर लेते हैं उसके बाद डिफरेंस देखेंगे। तो हम लोग LCAO पढ़ लेते हैं, कैसे कंबाइन हो रहा है LCAO, लीनियर कॉम्बिनेशन ऑफ एटॉमिक ऑर्बिटल कैसे हो रहा है वो देख लेते हैं। ओके, तो सपोज वी आर टेकिंग 1s, दिस इज 1s, और एक ले रहे हैं 1s, लेट अस टेक वन मोर 1s। If both electrons are in same phase, there will be constructive interference, bonding molecular orbital will be formed. But one is plus, one is minus, there will be destructive interference, you will get anti-bonding molecular orbital. So bonding molecular orbital, anti-bonding molecular orbital can give you sigma bond, can give you pi bond, can give you delta bond also. So sigma bond formed if it is bonding sigma bond, if it is anti-bonding sigma star, name we are giving. Pi bonding in valency bond theory can give you bonding molecular orbital pi, anti-bonding molecular orbital pi star. Delta bond will give you delta and delta star. Okay. So now when SS, 1s combined, this is SS overlapping, let us take. When SS overlapping takes place, we studied sigma bond, sidewise overlapping, head-on overlapping, pi bond, we studied, no. That we will study again in molecular orbital theory. That SS overlapping, this will mix means you get like this. We studied till this much. Till this much we studied, but we will study now further. What is that? Like this. So this is sigma SS, you can tell sigma SS. And the shape of these molecular orbital is bonding molecular orbital is oval shape. These are spherical shape, this is oval shape. This is not there in between. This is oval shape. Now if these two are mixing, means there is no constructive interference, there is destructive interference. If they are mixing, one is plus, one is minus, and it will give you like this, they will go away from each other. They will go away from one another. See, these are nucleus. Suppose two friends are there, but they have quarreled yesterday due to some problem, they have quarreled. And every day they are coming and sitting in the same bench. Okay, next day also they have to sit in the same bench, but they have quarreled. They are not talking with themselves, or they have to sit in the same bench. They have to sit in the same bench, then you will find in between them, suppose bag is there, or in between them some gap is there, and this boy is looking this side, left side, and this boy is looking right side, so they are not looking their faces because they have quarreled. So there is no bonding between them, there is a force of repulsion between them. So in between them gap is coming. But if they are friend, they have not quarreled yesterday, they have studied together, they are enjoying their compliments. So if they form bond, they will come closer. So one student will put his hands on shoulder of other students and they will sit together, even they will come very close to themselves, to one another. Isn't it? So if this is there, it will give you bonding molecular orbital, understanding or not? But if this is the case, it will give you anti-bonding molecular orbital, ABMO. Okay. So this is called sigma star. So this is called constructive interference. This is called destructive interference. Okay. Now let us see PP overlapping side by side. Head-on overlapping. Let first check. P is like this dumbbell. So this is plus, this is minus. Mixing with one more plus, and this is minus. So when they are mixing, then what will happen after mixing? Okay, they are overlapping. So this is also possible. This side is minus, that side is plus. So after overlapping, how they look. So during mixing, I'm not drawing, that you know. So after mixing, they will give you like this. So this is minus, this is minus, this is plus. And these two after mixing will be like this. This is plus, this is minus, this is minus, this is plus. So after mixing, there will be gap between them because there is force of repulsion dominant. This is force of repulsion dominant, this is force of attraction dominant. So when two electrons overlap, attractive force may be dominating or repulsive force may occur. So they will give you sigma bonding orbital for PP or sigma anti-bonding orbital for PP possible. So the lobe whichever coming together will be smaller and the other lobe will be bigger because force of repulsion dominant. And here the lobe whichever is mixing will be bigger and the lobe whichever not mixing will be smaller because they are coming closer. Is that clear?
Yes, sir.
So this is about sigma bond, sigma, sigma star, and this is also sigma and this is sigma star for PP. So next further I'll discuss in the next class. Okay. So next class I'll tell you how pi bonds are formed, how pi bonds, how delta bonds are formed, and by due to different type of overlapping. From this overlapping 2017 there was a question. Okay. JEE Advance. So let's stop. Okay, time is over. So I am closing now. Right?
Thank you, sir.
Okay.
Thank you.